and welcome to another WJEC A level physics question. This was question 6 from June 2012's Unit 4, and it's a question about resultant electric fields, which is still in Unit 4. So what we've got is 2-point charges of -6 and +6 microcoulombs arranged at points A and B. There's a third point X, making ABX into an equilateral triangle. And the first couple of parts of the question, we're asked to add arrows onto the diagram showing the directions of the electric field at X due to A, labelled EA, B, labelled as EB, and the resultant field labelled as ER. Now we've got to remember, to work out the direction of the field at X, we just visualise put in a positive charge at X. The positive charge at X would be attracted by the, -6 microcoulomb charge at A. So the field at the field at X due to A is pointing towards A, as in the diagram which I've already added to. Similarly, a positive charge at X is repelled by the positive charge at B, so EB would be in this direction, away from X. Those two fields will be basically equal and opposite in the vertical direction. Their vertical components will end up cancelling, but their horizontal components will end up adding together, so the resultant field ER will be basically directly to the left. Okay, for some reason I didn't want to scroll properly, but let's go back. So next, we're asked to calculate the magnitude of the resultant electric field at X, and we've got to show all our workings clearly. So let's first of all just calculate one of the fields, either EA or EB. They're going to be numerically equal to each other. So the formula for the field is 1/4 pi epsilon naught Q over R. 1/4 pi epsilon naught is 9 times 10 to the 9. The charge at A is -6 microcoulombs, but we can ignore the minus sign because we've already covered the negative part of it by the direction of the arrow for EA. And R here is 0.2 meters. Sorry, it's R squared over there, made a little mistake. So if we put that into the calculator, we end up with 1.35 meganewtons per coulomb, or if you prefer, you can use the unit of volts per meter. Now EB is going to be exactly the same size because it's the same distance away from a numerically equal, a +6 and a -6 of exactly the same microcoulombs in terms of their modulus of the charge, if you like. So EB will be exactly the same. Now if we wanted to find ER, one way of doing it would be to add together two lots of the EA, the 1.35 meganewtons per coulomb, times cos 60, add the two horizontal components together. So let's do it that way, and then I'll sort of mention a quicker way that we can do it. So what we've got is two lots of the 1.35 meganewtons per coulomb, both of them at 60 degrees to the horizontal. Now if you know your maths properly, cos of 60 is a half, so 2 times a half is 1, so we do end up with a final answer of 1.35 times 10 to the 6 newtons per coulomb. And it's to the left. I'll just put an arrow in there, just remembering that it's a vector quantity. Now the question only wants the magnitude, but I just put the arrow there for completeness. The slightly quicker way of doing it is to realise that all of the angles on the diagram are 60 degrees. So therefore we're going to end up with an equilateral triangle here. So if we put EB and EA tip to tail, we'd end up with ER being exactly the same size, because the sides of an equilateral triangle are all equal. Next we got some point Y, which is a distance 0.4 meters to the right of B, and we've got to calculate the electrical potential at Y. Well, the formula for electrical potential is 1/4 pi epsilon naught Q over R. So we've got 9 times 10 to the 9, and if we want to work out each of the individual fields, then let's do first of all VA. The charge there is -6 times 10 to the -6. Got to remember, with potentials we do need to include the minus sign because there's no direction to allow for that. And the distance from A to Y is 0.6 meters. So this time we're going to get an answer of minus 90,000 volts per meter. Sorry, just volts. 90,000 volts. hopefully we can see that this will cancel with that, leaving a 10 to the 3. 0.6 into 6 is 10, so we've got 90,000. You could do it on a calculator, obviously. VB similarly would be 9 times 10 to the 9 times plus 6 times 10 to the minus 6 over the distance of 0.4. So we can do that in the same way, and what we'll end up with there, the minus 6 and the 10 to the 9 cancel with a 10 to the 3. 6 divided by 0.4, or 60 divided by 4 is 15, and 9 15s is 135,000 volts, and this is a plus. The resultant potential, or the total potential, we just add those two potentials together, so let's call it VR, just in line with what we did in the earlier part of the question. Minus 90,000 plus 135,000 will give us 45,000 volts. And that's a positive because the 135,000 was positive. Next we've got to calculate the work done, or the work required to bring a small charge of 2 microcoulombs from a distant point to y. Well, if we understand that the definition of the potential at this particular point, y, is the work done in moving a unit charge from infinity to that point, then the work done in moving a different charge is simply the charge that we're moving, 2 times 10 to the minus 6, multiplied by the potential at that point, which we've already worked out as 45,000. There's actually a formula in the data book, which is basically that W equals Q delta V, which is what we've done here, because remember from a distant point, at a distant point the potential is 0. So this gives us an answer of 0.09 joules. And the final part of the question, we've got that small charge that we had, there's got a mass of 5 times 10 to the minus 3 kilograms. It's released at rest from the point y, and we've got to determine its speed when it returns to a distant point. So basically what's going to happen here is that all of the electrical potential energy that it had at y will become kinetic energy at infinity, because at infinity it's got 0 potential energy. So all we're going to do is equate half mv squared, the formula for kinetic energy, to 0.09 joules. So V is going to be the square root of 2 times 0.09, or you can have it as 0.09 divided by a half, that's exactly the same thing, over the mass of this charge, which is 5 times 10 to the minus 3 kilograms. Yes, 5 times 10 to the minus 3, just rereading that a second. And that will give us an answer of, going straight to this, the bracket is 36, so the final answer is 6 meters per second. Thank you for listening. Please remember to like and subscribe, and feel free to ask any questions. Goodbye.